This is a presentation of the paper with the title Strong Approximate Consensus Halving and the Borsuk-Ulam Theorem. My name is Kasper Høgh, and this is joint work with Eleni, Batziou and Kristoffer, Arnsfelt, Hansen. So first, let me talk a little bit about what is a consensus halving. So the problem of finding a consensus halving is a problem in fair division, where we have some resource that is modeled by the interval from 0 to 1. So throughout this talk, I'll call this resource a cake, and I'll denote the interval from 0 to 1 by A. And then there are a set of agents with utilities on this cake. And later, these utilities will be given as the distribution functions of the agents. So the value from 0 up to some point. Okay, and the goal then is to partition the cake into two parts, A plus and A minus, in such a way that all the agents value both the parts equally. That is, mu of A plus is equal to mu of A minus for the utility functions of all the agents. Okay, so let's see some examples. So here we have a case with three agents, and the first thing one might try to do is to place a cut down the middle and then give the left side the plus label and the right side the minus label. And doing this, we see that both the green and the blue agents are satisfied that both parts are valued equally, but the red agent will have too much value on the right side. But so one can just place a cut here and then give the labels plus, minus, plus. And then one sees that the part with the plus label is valued the same as the part with the minus label for all the agents. Okay, so here we could make do with two cuts, having three agents. This is another example with three agents, and here one sees that one really has to put a cut down the middle of each of the blocks. Because, for instance, if the red block didn't contain any cut, then the red block would be completely in the plus part or completely in the minus part. And then the red agent could not be happy that both the parts are equally valued. And it's the same for the other agents, of course. And one can, of course, generalize this construction to more agents. So for any number of agents n, one can make the same construction that requires n cuts. And Høgh and Rice showed that this is actually the worst that can happen. So they showed in 1965 that one may always partition the cake into two parts using at most n cuts, such that all the agents are satisfied that the plus part and the minus part are valued equally. Okay, so that was a little bit about the consensus halving problem. So now let me talk a bit about the Borsuk-Ulam theorem and show what is the connection between the two. So the Borsuk-Ulam theorem just says that if I have any continuous map from the n sphere to Rn, then there exists some point x such that f of x is equal to f of minus x. That is, there exists a pair of antipodal points that is mapped to the same point in Rn under the map F. And using this theorem, Simons and Høgh showed in 2003, or they gave a simple proof of the existence of a consensus halving. And the first thing, and the proof is so simple that I'll just give it here, it's just a couple of lines. So the first thing one notes is that any point in the n-sphere with respect to the one norm, so this is the sphere with respect to the one norm, so any such point corresponds to a division of the cake. So for instance, if one has the point minus 0.2, 0.4, minus 0.4, then it corresponds to the following division. So the first coordinate is minus 0.2, and so the first subinterval of the division has length 0.2, and it is given a label minus because the first coordinate is negative. So likewise, the second coordinate is 0.4, so the second subinterval of the division has length 0.4, and the label is plus because the coordinate is positive. And likewise for the last coordinate, its length, it corresponds to the subinterval of length 0.4, and it's given the positive label because the coordinate is negative. So now one wants to show the existence of a consensus halving using the Borsuk-Ulam theorem. So what we do is that we define a map from the n-sphere to Rn, where the ith coordinate function is given by the utility of the ith. So on some input, the ith coordinate function is given as the utility of the ith agent of the plus part of the division coming from this point x. So then the Borsuk-Ulam theorem tells us that there exists some x such that f of x is equal to f of minus x, which means that mu of the plus part of the division coming from x is equal to mu of the plus part coming from minus x. So what we want to show is that x is a consensus halving. And so we actually have to show that mu of a plus is equal to mu of a minus. But now, if one looks at the division coming from minus x, then all the cuts are placed in the same points. And the only thing that changes is that all the labels of the pieces change, or they flip. So therefore, one actually has that a plus of minus x is equal to a minus of x. And then we get from the above equality that x is a consensus halving. Okay. And so now let's give the actual definition of the consensus halving problem. So an instance of the consensus halving problem consists of a list of circuits that compute the distribution functions of the agents on the interval. And then, so it's a search problem, so we have to find some point x that is a consensus halving. And because of the previous proof, we choose the domain to be the one sphere, and then the set of solution consists of the x in the one sphere for which the following equality holds. And really, so on the left hand side, what we do is that we sum over all the coordinates that are positive. This corresponds to summing over all the subintervals that are given the positive label. And then what's inside the sum is just the ith agent's value of this subinterval. So the left-hand side is just the value of the plus part of the division coming from x, and likewise the right-hand side is the value or the utility of the minus part of the division coming from x. So that's the definition. And now, before I move on to state our main result, let's talk a little bit about related work. So we have already discussed these two existence results. So then we have some papers, one by Philosophes and Goldberg, where they consider the problem of finding an epsilon consensus halving. That is a division of the cake such that all agents agree that the two paces are almost of equal value. So we say that this is a weak approximation of a consensus halving. And they show that this problem is complete for the complexity class PPA. So later then, Philosophes, Hollender, Sotiraki, and Sambetakis simplified the above proof, and they also showed that even when the utilities of the agents are very simple, the problem remains hard. So then there's a paper by Delikas, Fernley, Melisorbus, and Spirakis, where they introduce a complexity class based on the Borsuk-Ulam theorem. And using the proof by Simmons and Su, they then show that the problem of computing an exact consensus halving lies in this complexity class BU. Now, our result deals with strong approximation of finding of consensus halvings. So for strong approximation, the problem is to find a division such that there is an actual consensus halving division x star such that the difference between x and x star is less than epsilon with respect to the infinity norm. So the difference in every coordinate is at most epsilon. And we then show that the problem of computing a strong approximation of a consensus halving is equivalent to computing a strong approximation of a Borsuk-Ulam point. Okay. Now, in our reduction, we actually consider a variation of the Borsuk-Ulam theorem. So the Borsuk-Ulam theorem is equivalent to the following theorem that we call the Borsuk-Ulam theorem. And it says that if we have a continuous map now from the n ball to Rn that is odd on the boundary, then there exists an x such that f of x is equal to 0. And in the paper, we show that the complexity class of corresponding to finding strong approximations of Borsuk-Ulam points is equivalent to the complexity class of finding strong approximations of zeros of these maps from the Borsuk-Ulam theorem. And therefore we make the reduction from this BBUA. So to recap, we have some f from the n ball to Rn, and we have some epsilon greater than 0. And now the goal is to find a strong approximation of a 0 of f. And to do this, one can show that it actually suffices to find an x such that the infinity norm of f of x is very small, doubly exponentially small in the parameter epsilon. Okay, so first let me give an overview of the reduction. So we have this f and we have this epsilon, and we want to find a strong approximation of a 0. And we want to reduce this problem to strong approximations of consensus halvings. So what do? We construct a consensus halving instance as follows. So the idea is to use agents to simulate the function f. And all these, so we simulate f a number of times, so 2n plus 1 times, and I'll explain why later. And these simulations, they then output the results of the circuits. So they output f1 of x up to fn of x, where x is some input. And then we have n so-called feedback agents, and these agents check that the coordinate functions of f are all less than or equal to delta in numerical value. And but I haven't yet explained what is this input that is given to the simulations of f. Well, so this input is actually encoded by the feedback agents, because so all the agents simulating f, they will make cuts in known intervals. So they will all make exactly one cut in a specified interval. But the feedback agents, they can place cuts anywhere. And the hope is basically that they will place cuts all the way to the left, where I have written these x1 up to xn. And then these cuts will encode some values, these x1 up to xn. And it is these values that is read in by the circuit, that is read in by the agent simulating f, and then output into the feedback region. Okay, so that's sort of an overview. So let's look a bit further into the reduction. So I said that some values are encoded all the way to the left, but how are they actually encoded? So they are encoded by what we call the label encoding. So for instance, here we have this x1 where we have 2 cuts in the first interval, and perhaps the small sub-intervals of plus with the plus label, they are perhaps of length 0.2, both of them, and then the minus will be of length 0.6. And then the value that is encoded here, that will be 0.4 minus 0.6, which is equal to minus 0.2. And why is that? Well, because the label encoding is just defined as the part of the interval that has the plus label minus the part of the interval that has the minus label. And this is just the Lebesgue measure. And now we want the circuits to read in these values. So how should they read them in? Well, so before each circuit, we will have a sign detection region which will detect whether what the label is immediately before the circuit. And so, for instance, here we see that the sign detection interval, it detects that the label is plus. So what we want to read in here is actually, we want to read in simply x1. So to ensure this, we place this small blue agent that flips the sign. And then there has to be a cut in this little square here, which is 0.4 in. So we have placed an agent now that has a block over x1 and then a block over this SI x1. And then it also has these two red rectangles, and that's just to force a cut in this interval. So now, because there is 0.4 with plus label in the x1 all the way to the left, there will have to be 0.4 in the minus label over to the right. And that's because this agent will should value the plus part and the minus part equally. So that's why this cut will be placed like that. And now, what value is encoded now? Well, inside the circuits, we encode the values differently. So there we encode values assuming that there's only one cut in each unit interval. And then we can encode values by taking the length of the first subinterval and then minus the length of the second subinterval. So what will be encoded here? It will be 0.4 minus 0.6, which is minus 0.2, which is S1 times X1, which is what we wanted to encode. Now, if there's a negative sign, well, then what would happen would simply be that we would place that the cut would be placed at 0.6 into the interval, and then we would encode the value of 0.2, which would be minus x1, which is what we should encode in this case. So the point of this is that we want the circuits to either read in x or we want to read in minus x. And the reason for this is because this sign detection, the reason why we do this is simply because this allows us to use the boundary condition at the very end of the reduction. So it will probably become clear why we do it in the next slide. So let's see, what do we do? So we now construct a consensus halving instance as described before, where we simulate f 2n plus 1 times. And the parameter we give for the strong approximation is epsilon over 4n. And the reason for this is the following. So now we can find some strong approximation of an exact consensus halving to this consensus halving instance. Call this exact solution Z star. Now, when the infinity norm difference between Z and Z star is less than epsilon over 4n, this ensures that the points encoded by Z and Z star, which we denote by x and x star, they then satisfy that the difference between x and x star is less than or equal epsilon half. So now it actually suffices to show that x star is epsilon half close to an actual zero of f, because then x will be epsilon close to an actual zero of f by the triangle inequality. So to show that x star is epsilon half close to an actual zero, it suffices to show that the infinity norm of f of x star is less than delta for a sufficiently small delta. And this delta we can compute inside a circuit and use, because it's subtly and exponentially small in epsilon half, so we can just use repeated squaring. So if there are no stray cuts, and what do I mean by this? I mean if all the cuts are placed in the coordinate where we encode the coordinates, then we show that all the simulations work and the feedback agents actually force fi of x star to be 0. It should be fi of x star. Now, if there is a stray cut, then it means that there are only any feedback agents. So if there is a feedback agent that doesn't place a cut in the coordinate encoding region, then there must be one coordinate, one subinterval where there's no cut. And this means that the value encoded in that by that interval will be either +1 or -1. And this means that the point encoded lies on the boundary. So therefore f of x is equal to minus f of minus x. Okay, so now let us assume that, and sorry, all these should actually be x stars. But anyway, so let's assume that fi of x star is greater than delta. So we know that there can only be n stray cuts, or there can be there are n feedback agents, and each feedback agent can corrupt only one circuit. So there are n+1 circuits that read in the correct value that is encoded, and they work correctly. So they will all output the right thing. So now if there is a plus, so here on the left side, I have drawn a circuit where there is a plus in the sign detection region. And then the labeling sequence in that whole circuit will be minus plus all the way. In all the subintervals there will be minus plus. And also it will output the correct thing. So it will output fi of x star. And this is greater than delta. And then the way these feedback agents are constructed is they have a very narrow block centered around 0, and it's only delta wide. So when the value output into that region is larger than delta, that means that this block will be in the minus part. Conversely, if there is a minus in front of the circuit, then the value read in will be minus x star. But we know that f of minus x star is minus f of x star, and this is now less than delta. So therefore the cut will be placed now all the way to the left of the little block. But when there is a minus in front of the circuit, then the labeling sequence in the circuit will be plus minus. So therefore in this case, this narrow block will be also in the minus part. But what does this mean? This means that we have n+1 of these blocks that all have the same label, namely minus in this case. But there are only n remaining blocks for this feedback agent, and so it cannot cancel out, there cannot be enough value in the plus part of the division for this agent to be happy that it is a consensus halving. So therefore we reach a contradiction, and we conclude that fi of x star is actually less than delta for all I. And now this shows that x star is actually epsilon half close to an actual 0 of f. And so x is also epsilon close to an actual 0 of f. Okay, so that was the reduction, and that was all I want to say. So thanks for listening.